Hey, in this video we will talk about a t-test simulation, and the main topic what brings this up is the idea of a trend and identifying whether or not there is a permanent linear trend in a data set, or whether on the other hand it's just a temporary time period where it appears that there's a trend and sooner or later it's going to reverse its direction or it's going to flatten out. And that's a tough question in a data set when you have a limited number of values, a limited number of time points. It's just hard to know. If you were able to extend time out, you'd have a better chance of being able to tell whether or not it appeared that that trend were going to be permanent or not. So it's a really tough situation. So with that, we will go over to PowerPoint and look at the PowerPoint presentation that's titled a t-test simulation. Now, first thing, let's talk about a couple of questions here that brings this up. We sort of alluded to it in the introduction there, but the relevant questions are this. How often does the standard t-test, now let me take a time out there real fast. The standard t-test, I'm talking about the one that you learned in an intro stat class when you'd never heard of time series analysis. You were just talking about a regular data set that's not where the data does not depend on time, and it's just the standard setting, the usual setting. What would happen if you used the standard t-test to tell whether or not there's a linear trend in a time series realization? Now, this time series realization is going to actually be a stationary AR1 realization. And remember, a stationary realization by definition means that there's a constant mean. A constant mean implies that there is no trend that depends on time. Because if it's a constant mean, that means that the mean doesn't depend on time. So the question is, how often does this standard t-test make a mistake? Meaning, how often does this standard t-test say that yes, there's a trend in a data set that we know there's not? There's the question. And very related to that is, how important is the uncorrelated assumption when using the standard t-test? SLR standing for simple linear regression. But if you use the standard t-test, how important was that assumption that you learned when you first took an intro stat class, when you heard that the errors need to be independent? For us, we're saying uncorrelated. So how important was that really? And that's what the simulation is going to reveal to us. So let's go ahead and set up the simulation. In order to conduct a simulation, you need to have a beginning model. The actual model is, remember we said it's going to be a stationary AR1 model. And it looks like this. X sub t equals 10 plus zt, where zt is defined as a zero mean AR1. A zero mean AR1 with these phi values, these phi1 values. There's only one phi1 because it's an AR1. With phi1 values of 0.8, 0.9, 0.95, and 0.99. Notice that all of those are less than 1 in absolute value. That means that it's a stationary model. And if it's a stationary model, that implies that the mean is constant. That means that there is no trend here. And as we said earlier, we're going to see how many times the standard t-test accidentally and incorrectly says that there is a trend. So here's what we do. We consider three different realization lengths. N equals 100, N equals 200, and N equals 500. And we're going to simulate 1,000 realizations from each of those combinations. What combinations do I mean? Well, remember, we've got four phis, 0.8, 0.9, 0.95, and 0.99. But we want to check those at these three different realization lengths of 100, 200, and 500. So there's our 12 combinations. And we'll run 1,000 realizations for each of those 12 combinations. And we'll see how this test does. Now remember, this test, it's a hypothesis test. The null is that there is no linear trend because that's B1 equals 0. And the alternative is the opposite. That's that B1 is not 0. That means that there is a linear trend. Now remember, this B1 is just the slope coefficient. So if you have a slope of 0, what that's saying is that there is no trend. There's no, meaning that the data points are all scattered about, and there's just because the time period is high, or if you go deeper into the data set, or if you look earlier in the data set, that doesn't give you an indication about whether or not the value is going to be high or low. It's just a slope of 0. That's what we mean by no linear trend is present. Just like it was back when you first looked at simple linear regression. All right, so let's take a look at this. There's your test. The question that we're really asking is how many times is our test going to reject that null when it shouldn't? Because recall, if this is a stationary model, and it is, we know that the way that this was defined, it's a 0 mean, we know that B1 is supposed to be 0. So we hope that we're not rejecting this very often. Now we need to set our alpha, and we'll talk about that on the next slide. So here are your results. We're going to set that alpha at 0.05. Remember, alpha is the probability of a type 1 error, and that's defined as the probability of rejecting a null that is true. Let's go back one slide. Rejecting a null that is true. That means we're rejecting this null and saying that there is a linear trend, when really the truth of the matter was there was no linear trend present. That's what we're talking about as far as the type 1 error and alpha. So we're setting that alpha to be 0.05. That's what we call the nominal significance level. Our nominal significance level is 0.05. That means that 5 out of 100 times we're going to possibly have an error. We're going to reject a null that we shouldn't have. Okay, well, let's look at our simulation results. So that means that in this table, throughout this table, we're expecting things around 5% if this test is working the way it should. And one quick glance tells you they're nowhere close to 5%. So let's look at this. On the left column, we've got n equals 100, n equals 200, n equals 500. Across the 4 rows, we've got the different phi values of 0.8, 0.9, 0.95, 0.99. Notice that those values are getting closer and closer to 1, right? Closer and closer to the unit circle. And it appears that that causes the test trouble too. So let's look at that first column of phi 1 of 0.8. Looks like for n equals 100, 200, and 500, we have values. This is probability of rejecting the null when the null is true of 50.6, 50.8, 53.1. That's terrible, terribly high. We were hoping that would be 5%, and it's not even close. If for phi 1 equals 0.9, it's even worse. We're in the 60s. For phi 1 of 0.95, even worse. We're in the 70s. And for phi 1 of 0.99, in the 80s, upper 80s, and 90. So just terrible. The test is performing miserably. What's happened here? What is going on? Well, remember, the standard t-test had an assumption that we better not ignore, and that assumption was that the errors are independent. That is uncorrelated. But we know that in a AR1 model, we know that there's a correlation structure. There's a dependence. So we have violated an assumption, and that's what has thrown the test off. Okay, here's an interpretation of the results. We've already talked about these, maybe not in detail, but let's just kind of review here. So as we said, the test should have rejected the null in about 5% of the 1,000 replications. That's because we set the nominal significance level to be 0.05. By the way, let me go back one slide. These values in the table are called the observed significance levels. The nominal level was 0.05, but our observed significance levels were what we see in the table. For a test to be performing the way we would like, we hope that our observed significance level is close to our nominal significance level, and we didn't have that. Okay, so what just happened to us? Well, we ended up rejecting that null way more than we should have rejected the null. And what does that really mean in English? The fact that it rejected the null when it shouldn't have? It was saying that there is a linear trend in the data, a permanent linear trend, that is a permanent deterministic linear trend that this test says is going to go on forever. Because why? Well, it saw what it viewed as a linear trend, and it thought that it was going to go on permanently, when really it was just a temporary time period in which the points did have a linear sloping upward or downward trend. So what happened? Why did it fail so badly? As we've been saying, well, the errors are correlated, and the standard t-test assumes that they're not, and it confused it. It tricked it into thinking that the trend was permanent when really it's not. Okay, here are some more interpretations. The obvious, the finding of a significant slope, that is, concluding that B1 is not 0, when using the standard t-test on time series data, cannot be trusted. So if you use the standard t-test, the one that you learned in a non-time series setting, on a time series data set, those results can't be trusted. Just because you reject that null, that doesn't mean that that trend is a deterministic permanent trend. We saw it in our simulation here. So here's what else this means. That means that that assumption that we did learn back in early stats classes in a non-time series setting, that assumption about having the error terms, the residuals, to be independent, that is uncorrelated, that is a really big deal. And here's the tricky part of all this. It's very possible, very probable, actually, for positively correlated time series data to show trending behavior. It may just not be permanent, but show trending behavior even in the absence of an actual deterministic trend. And that makes this tricky. There's no doubt about it. As I said, here's what we wish. If we had our wish list, we could say, well, could we extend that another 50 years and let me take a look at it longer? And the answer to that is usually no. So you have to make a judgment call. You have to make a decision on the data that you have. And that can really be a tricky proposition. And the problem is it's going to influence what type of model you use to model the data, and that's going to make a big difference in your forecast. So this is a tough situation. So what do we do? Well, obviously this is, again, follows the obvious point from the slide before. Well, if the residuals, if you suspect that they're even slightly correlated based on a plot, maybe your eyes tell you that, or some other test that we have, then don't use the standard t-test to test for the slope of B1, because we've seen that it can be highly inaccurate. Then what do you do instead? Well, what we need is some test to test for that slope term that somehow takes into account, that means that it adjusts for the correlation in the residuals. And that's what we're going to spend some time doing in the remainder of this chapter. I've got another video coming up where we have looked at a method that does take into account the correlation in the residuals, and I think you'll be impressed with its numbers. So we'll look forward to seeing you back again in that video.